Hi everyone, in this video we are going to learn how to find the solution of homogeneous recurrence relation with a constant coefficient. Before that we will learn what is a general form of the recurrence relation with the constant coefficient that is given in equation 1. So here we have taken the recurrence relation where an is defined in terms of n minus 1 term, a n minus 2 term, a n minus 3 term, a n minus k term, and something is extra that is represented by fn. And all these c1, c2, c3, ck are the real numbers. And here we have taken the condition that ck is not is equal to 0. It means we have used k terms from the sequence. First term, second term, third term, and it is a kth term to calculate an. Now, based upon the Fn, we can call this recurrence relation as a homogeneous and non-homogeneous if Fn is equal to 0. It means अगर ये Fn term 0 हो गई, आप sequence को calculate कर सकते हो with the help of previous terms only. Then it is called as the homogeneous recurrence relation. Whereas if this fn exists means if it is not is equal to 0, maybe it is 1, maybe 2, maybe n square, 2 raised to power n, sine, cos. In that case, this recurrence relation is called as the non-homogeneous recurrence relation. It's like if we want to calculate the sequence from this recurrence relation, we need something extra that is not depending upon the sequence term. In that case, it is called as a non-homogeneous recurrence relation. Now, this is also called as a linear recurrence relation. Why? Linear means power is 1 and quadratic means power is 2. Now, in this case, we call it as a linear. There is a reason. First thing is power of the sequence terms are 1. If you observe in this case, an power is 1, an minus 1 power is 1, an minus 2 power is 1, an minus 3 power is again 1, an minus k power is 1. There is no need to figure out for the function fn. Maybe it is linear, maybe non-linear, maybe quadratic, cubic, anything. But we need to observe the powers of the sequence terms only. Second condition is product of the sequence term is not allowed. Sequence terms को हमें सिर्फ add किया है with the help of the constant. We have not multiplied them. That is called as a linear combination of sequence term. Due to this, it is called as the linear recurrence relation. So two things we need to check: the power of an minus 1 up to all n minus k is 1. Second thing, product of sequence term is not allowed for to call it as a linear recurrence relation. So if both the conditions are valid, we can say that it is a linear recurrence relation. And next point is a degree. In this case, the degree of this recurrence relation is k. Now, how to predict that the degree is k? Degree is calculated. Just take the lowest index and the maximum index from the recurrence relation. In this case, the maximum index is n from here because it is a maximum value here, and the lowest index is n minus k. Take their difference, n minus k. This is equal to k. So its degree is k. According to the degree of recurrence relation means an is calculated in terms of previous k terms of the sequence. नेक्स्ट टर्म को कैलकुलेट करने के लिए बेसिकली हमें k टर्म्स चाहिए सीक्वेंस की. दैट्स व्हाई इट इज कॉल्ड एज अ डिग्री एज k. Now, with the help of these examples, let's identify whether the recurrence relation is linear, homogeneous, and what is a coefficient, and at last, what is degree. In this case, it is a recurrence relation that is given in terms of p. So you can check it whether this is linear or not. For the linear, power of the sequence term must be 1. Second, product form of the sequence term is not allowed. And both the things are valid in this case. So we can say that this is clearly a linear recurrence relation. Let's check it for the second case. Again, in this case, the power is 1, power is 1, power is 1, not in a product form. So clearly this is linear. In the next case, an, its power is 1, an minus 5, again its power is 1, so it is linear. Next, an, we just need to figure out for the an, not for the constant. Only for the sequence term, we need to check whether the power is 1 or a not. And they are not in product form. It follows both the condition, it means it is a linear. Hn raised to power 1, hn minus 1 raised to power again 1. They are not in a product form, it is clearly linear. Here, an minus 1, yes, linear because power is 1, not in a product form. An raised to power 1, an minus power is 2. So this is not a linear. In this case, an power 1, an minus 2 power 1, an minus 1, an minus 2, their powers are 1, but they are in a product form. Due to this reason, this is not a linear. Next case, an raised to power 1, an minus raised to power 1. So do not get confused with the coefficient. We just need to figure out for the power. Powers are 1 and they are not in a product form. So clearly this is a linear. Next, we need to identify which one is the homogeneous. As per this one, so we need to check whether there is any extra term apart from the sequence term. So no extra term is there. It is Pn minus 1. So clearly this is homogeneous. It depends upon the sequence term. Fn minus 1, Fn minus 2. No extra term is there. Homogeneous. An minus 5. No extra term. Homogeneous. In the next case, an sequence term, and the next is not a sequence term. Something is extra, that is 3. So clearly this is not a homogeneous, we call it as a non-homogeneous. In the next case, hn minus 1, and the next term is not of the form h. So there is a one constant that is extra. So it means it is not a homogeneous, means non-homogeneous. In the next case, an minus 5, and the next is a n square. So this is not depending upon the sequence term. So clearly this is not a homogeneous. So it is non-homogeneous. In the next case, nothing is extra. So we can call it as a homogeneous. Even in the case of H and I, both are homogeneous. Everyone is depending upon the sequence term. Next, we need to identify the coefficient. What is the coefficient of the sequence term? In this case, the coefficient is 1 and here 1.111. So it means coefficient is constant. Next, coefficient 1, 1, 1. So all the coefficients are constant. So we can call it as it is a recurrence relation with constant coefficient. Here coefficient is 1. Here coefficient is again 1. So constant coefficient. Here coefficient is 1. There is no need to look for this case. This is only for the non-homogeneous case. So its coefficient is 1. Again we can call it as a constant coefficient. In this case, what is the coefficient of Hn and Hn minus 1? They both are having a constant coefficient. And F part, again constant coefficient as a 1, 1. In this case, coefficient is 1. Coefficient is 1. So constant. Next case, constant. In the next case, its coefficient is 1 and its coefficient is n. Now it is varying. With the help of n, we can vary the coefficient. It is not the fixed one, means not a constant, or we can say that variable coefficient. Next, we need to deal with the degree. For the degree, we need to take the lowest index and the maximum index. Maximum index in this case is n and lowest is a n minus 1. What is the difference between these two? 1. That is 1. So it means its degree is 1. For the case B, maximum index is n. This is n minus 1, n minus 2. Lowest index is n minus 2. Difference between these two one is 2. So it means degree is 2. In the next case, an, that is the maximum index, an minus 5, lowest index. What is the difference between these two one? That is 5. Its degree is 5. Next is an is equal to 3. Maximum index is n. Lowest index is again n. So n minus n is 0. So it is a recurrence relation with the degree 0. Next case, n minus 1. Difference is 1. Next n minus 5, 5, n minus 1, 1. Next n minus 2, n minus 1, n minus 2. So lowest index क्या है? n minus 2 and the maximum is n. Difference is 2. And in the next case, degree is 1. So from here we can call it as it is a linear recurrence relation, homogeneous with constant coefficient having a degree 1. Like in the D part, we can say that linear non-homogeneous with constant coefficient with degree 0. Whereas in the ith part, we can say that linear homogeneous recurrence relation with variable coefficient having a degree 1. So this is how we can identify whether the recurrence relation is linear, homogeneous, and what is the coefficient, and after that we can calculate its degree. Now we are taking the case of solution of linear homogeneous recurrence relation with constant coefficient. And here we have taken the recurrence relation, that is a homogeneous recurrence relation, means that Fn is equal to 0 in this case. And the recurrence relation degree in this case is k, because we have imposed the condition that ck is not is equal to 0. It means definitely this term is there. And the difference between the highest and the lowest index is k. So it means it is a recurrence relation with degree k. Also, this is a linear. You can check it. The power is 1 and they are not in a product form. Whenever we are dealing with a linear homogeneous recurrence relation, we assume that it has the solution of the form r raised to power n. So let it be a star equation. So if r raised to power n is the solution of this recurrence relation, it means it will satisfy this one. Satisfy means in place of an we can fix r raised to power n, and in place of an minus 1 this becomes r raised to power n minus 1, and in place of an minus 2 power is n minus 2. In case of an minus k, r raised to power n minus k. So after substituting an is equal to r raised to power n, we have this form. Now take all these terms on the left side, means we will collect all these terms in one side. So we have negative of C1, negative of C2 along with this term, negative of C3 along with this, negative of Ck along with this is equal to 0. Obviously this term will be also a negative. Now it is r raised to power n form. Here it is r raised to power n minus 1, r raised to power n minus 2, r raised to power n minus k. So it's like this, r raised to power 4 minus r raised to power q, r square is equal to 0. Now in this case, what you will do? We will take r square outside. So we have r square minus r minus 1 is equal to 0. The same procedure we will follow here. We will take lowest power outside. Lowest power is n minus k. So before that, we can create n minus k here by just writing minus k plus k. Even in this case, minus k plus k, minus k plus k in this case, even for this case, and here there is no need to write this one because it is already in n minus k form. Now we can take r raised to power n minus k common. So we have r raised to power k, r raised to power k minus 1, r raised to power k minus 2, r raised to power k minus 3, and this is already outside, so simply constant is here. Once you do that, whatever the equation we have in the bracket form, that is called as the characteristic equation of this recurrence relation. That is r raised to power k as it is, negative of c1, r raised to power k minus 1, so on, put it as equal to 0. Now it is an equation whose power is k, so definitely it has a k roots, and that roots are called as the characteristic roots. Based on the characteristic roots, we can write the general solution for this homogeneous recurrence relation. How to write that one? The first case is when the roots are real and distinct. जब भी आपके पास roots and real and distinct होंगे, as for this one, we have taken the k roots because we are getting a characteristic equation with power k. So we can write the solution as first constant, first root raised to power n, plus second constant, second root raised to power n, plus third constant, third root raised to power n, so on. And here we have taken the k roots, so we can write kth constant k root raised to power n. Case 2 is when the roots are equal, means they are real and equal. So in that case, what we can do, in place of R2, we can replace it by R1. Even R3 is get replaced by R1. RK is also replaced by R1. But we need to create a different roots. So for that, we need to multiply first with n, then n square, then n cube, till n raised to power k minus 1. When the roots are same, so we need to create a different root. For that we are multiplying by the index. तो यहाँ पे root एक बार repeat हुआ था, so we are multiplying by n. Now again it is getting repeated, so again multiply by n, we will get a n square. Then again multiply by n, that will be a n cube, and so on. And third case is when the roots are complex. Complex means x plus iota y form, x minus iota y, and the complex roots occur in a conjugate pairs. So it's a plus iota, here it is a negative iota. In this case, first we will write the solution of the recurrence relation in the case of 1. As they are distinct roots, we can write first constant, first root raised to power n, plus second constant, second root raised to power n. After that, we will convert this into the r theta form because we need to eliminate iota. So for that we can write this as is equal to r raised to power n constant times of cos n theta plus some new constant times of sin n theta. Now what is r in this case? R is basically a distance from the origin. That is, r is equal to under root x square plus y square, where cos theta is equal to x by r, sin theta is equal to y by r. Now how we are getting this one? It's a very simple. The reason is when we are dealing with the Cartesian plane, suppose this is xy plane, and we need to convert into the r theta form, means if this point is x comma y, r is the distance from the origin, and theta is with the x-axis. So in this case, we can write here it is a right angle triangle. This point is x and this is y. So according to the right angle triangle, we can write cos of theta is equal to base upon hypotenuse, that is r. From here we are getting x is equal to r cos theta. And for the sin theta, that can be written as perpendicular, that is y, upon hypotenuse. So from here we are getting y is equal to r sin theta. Basically we are using a polar coordinate. So x is replaced by r cos theta, y is equal to r sin theta. So put it here, we have a is equal to constant. This is r cos theta plus iota r sin theta raised to power n plus c2 r of cos theta minus iota times of r sin theta raised to power n. From here what we can do, we can take r outside. So we can write first constant r raised to power n cos of theta plus iota sin of theta raised to power n, plus second constant, again take r outside, so we have r raised to power n cos of theta negatives of iota sin theta raised to power n. This is equal to, now r raised to power n we have in this case as well as in this case, so we can write r raised to power n outside. C1, this can be written as e raised to power iota theta raised to power n, plus second constant, this can be written as e raised to power of negative iota theta power n. This is further is equal to r raised to power n, first constant e raised to power iota n theta plus second constant e raised to power negative iota n theta. that is further is equal to r raised to power n. Now expand this angle as n theta now. Even in this case, negative of n theta. So we can write this constant as it is. So in place of this, we can write cos of n theta plus iota sine of n theta plus c2, and in place of this, we can write this. Now simply collect the coefficient of cos n theta. So you will get C1 plus C2. That is a new constant that is mentioned here as a. Coefficient of sin n theta, that is iota times of C1, and here negative iota times of C2. That is another constant. Let it be a B. And the rest of the things are as it is. So here R represents the distance from the origin, that is under root x minus 0 whole square, that is x square, plus y minus 0 whole square, that is y square. Cos theta we can expand from here. The value of cos theta either you can write in this format or you can evaluate from the polar coordinate, that x is equal to r cos theta, means cos theta is equal to x by r and sin theta is equal to y by r. Here we have taken the first example. Find all the solution of this recurrence relation with a0 is equal to 2 and a1 is equal to 7. First step in this case is we will take an is equal to r raised to power n is the solution of this recurrence relation. Means in place of an we will write r raised to power n. In place of an minus 1, that is r raised to power n minus 1. In place of an minus 2, it is r raised to power n minus 2. After that, we can take all these terms on the left side and we can write r raised to power n minus r raised to power n minus 1 minus double of r raised to power n minus 2 is equal to 0. Now the lowest power is r raised to power n minus 2. So divide by this lowest power. So we have from here r square minus r minus 2 is equal to 0. What we have done in this case, either you can take r raised to power n minus 2 outside, or we can say divide this with r raised to power n minus 2. That is the lowest power. And here we have simply r square. In this case, it is written as n minus 1 minus n minus 2. So this minus n is get cancelled. It is minus 1 plus 2. So we are getting simply 1. So it is the power of r. Same in this case, that is get cancelled. We are getting as a 2. There is another way to write this one. Observe the degree of this recurrence relation. So in this case, the degree of this recurrence relation is 2. Maximum index is n and the minimum index is n minus 2. Take their difference, that is 2. It means maximum power we have as r square. Next index is reduced by 1. It means its power is further reduced by 1. And here this is further reduced by 1. Again we will reduce the power. Now we need to find the root for this case. So from here we can write this is negative of 2r plus r. From here take r outside, we have r minus 2 plus r minus 2. So this is r plus 1, r minus 2, and we are getting the value of r as 2 and minus 1. Now the roots are real and distinct. So in this case, how to write the general solution? That is first constant, first root raised to power n plus second constant, second root raised to power n. So this is how we need to write the general solution of this recurrence relation. But now in this question, it is given that a0 is equal to 2 and a1 is equal to 7. It means with the help of this, we can evaluate the values of constant C1 and C2. For a0 is equal to 2, it means here n is equal to 0. Substitute n is equal to 0 in this case. We have a0 is equal to C1 2 raised to power 0 plus C2 minus 1 raised to power 0. This implies A naught is equal to C1 plus C2, and the value of A naught is 2. So we can write in this case 2 is equal to C1 plus C2. Next condition we have A1 is equal to 7. It means for A1 is equal to 7, we can substitute n is equal to 1 in this relation, because here we have A1 is equal to 7. For this, we have A1 is equal to 2 times of C1, and when you put n is equal to 1, we are getting a negative of C2. So from here we are getting 7 is equal to double of C1 minus C2. Add these two 1. So we have 2 plus 7 as 9 is equal to 3 times of C1, and the value of C1 constant is equal to 3. Substitute in the first case, we have 2 is equal to 3 plus C2. This implies the value of C2 is equal to negative of 1. Now the final solution is C1 value is 3, 2 raised to power n, and C2 is negative of 1, it is minus 1 raised to power n. This is the final solution of the recurrence relation. This with condition A naught is equal to 2 and A1 is equal to 7. Next question we have, find the explicit formula for the Fibonacci numbers. Now what do you mean by Fibonacci numbers? Basically it is a sequence of the form whose elements are 0, 1, 1, 2, 3, 5, 8, 13 and so on. From here you can observe it is a sequence where a particular term is calculated with the help of previous two 1. That is, sum of the previous two terms is equal to the next term. Even in this case 5 plus 8 is equal to 13. Like here 1 plus 1 is equal to 2. 1 plus 2 is equal to 3. But this 1 and 0 cannot be calculated with the help of its previous two terms, because previous two terms does not exist. So in this case we can directly write the recurrence relation. For that we can take, let f of n be nth term of Fibonacci sequence. It means f of n is calculated as f of n minus 1 plus f of n minus 2, where we take the first two numbers as a first condition f of 0 is equal to 0, f of 1 is equal to 1. So it means we can calculate f2 from here. So we can say that n is equal to 2, 3, 4 and so on. Now we need to find the explicit formula for this Fibonacci numbers. It means we need to find the solution of this recurrence relation. So first step is we will take all these terms in one side. So we can write f of n minus f of n minus 1 minus f of n minus 2. This is equal to 0. Now we know that for the homogeneous recurrence relation, we have the solution of the form r raised to power n. So we assume let fn is equal to r raised to power n is the solution of recurrence relation. So if it is a solution, definitely it will satisfy this one. So we can write r raised to power n here, r raised to power n minus 1 minus r raised to power n minus 2 is equal to 0. We can directly write the characteristic equation from here. How to write that one? First step, we will find the degree of this recurrence relation. In this case, the degree of this recurrence relation is 2. So maximum power of r in this case is r square, that is the degree of the recurrence relation. Then this power is reduced by 1. So we can reduce this power again by 1 minus this power is further reduced from here to here by 1 or from here to here by 2. So we can write r2 minus 2. This is equal to 0. Simplify this. This is r square minus r minus r raised to power 0 is 1 is equal to 0. Now we need to find the root of this quadratic equation. As we have the general formula for the quadratic equation ax square plus bx plus c is equal to 0, the root of this quadratic equation is calculated as minus b plus minus under root b square minus 4ac by 2a. Now what is the value of a in this case? That is 1, and the value of b is minus 1, and the value of c is equal to minus 1. So according to this formula, the roots is equal to r is equal to minus of minus 1 plus minus under root minus 1 square minus 4, a is 1 and c is minus 1 divided by 2 into a. This is equal to negative negative is a positive plus minus under root minus 1 square is 1, negative negative is positive 4 by 2. This is equal to 1 plus minus under root 5 by 2. It means from here we are getting a two roots. One is 1 plus root 5 by 2 and second is 1 minus root 5 by 2. Now the point is whether this is a real or a complex. It is a real number. There is no iota form. So in this case, we can write the solution as fn is equal to first constant, first root raised to power n plus second constant, second root raised to power n. This is kind of explicit formula as per this recurrence relation. But we need to deal with these two conditions as well. Means when f of 0 is equal to 0, f of 1 is equal to 1. According to this, find the values of constant. So for that, what we need to do, we will observe the condition. It says that f of 0 is equal to 0. In this case, the value of n is 0. So plug n is equal to 0 here. We have f of 0 is equal to c1. Constant raised to power 0 is 1 plus c2. Constant raised to power 0 is again 1. So this implies c1 plus c2. This is equal to f of 0, that is equal to 0. So this implies c1 is equal to minus of c2. Now take the second condition. It says that f1 is equal to 1. It means we will plug n is equal to 1 in this form. So we have f1 is equal to c1. Put n is equal to 1. We have 1 plus root 5 by 2 plus c2 1 minus root 5 by 2 power 1. Now here we have c1 is equal to minus c2. So we can write in this case in place of c1 as minus c2. This is as it is plus c2 1 minus root 5 by 2, that is equal to f1 and the value of f1 is equal to 1. Now we can take c2 outside. We have negative of 1 by 2, negative of root 5 by 2, and here positive of 1 by 2, negative of root 5 by 2. This is equal to 1. So this number is get cancelled with this one. It is a double of this. So from here we can write c2 of 2 times of root 5 by 2 with negative sign. That is minus root 5 by 2 minus root 5 by 2 is equal to this. This is equal to 1. 2 is get cancelled with 2. This implies c2 is equal to minus 1 by root 5. It means the value of c1 is equal to, that is a negative of c2, it is 1 by root 5. So this implies The explicit formula for Fibonacci sequence is plug the value of constant here, that is Fn is equal to C1 value is 1 by root 5 into 1 plus root 5 by 2 raised to power n plus C2, and the C2 is equal to minus 1 by root 5. So we can write minus 1 by root 5, 1 minus root 5 by 2 raised to power n. And this is the final answer in this case. Taking next example, we need to solve this recurrence relation where a0 is equal to 1 and a1 is equal to 6. So first step is we need to write the solution is of the form r raised to power n. It means it will satisfy this recurrence relation. In place of an we can write r raised to power n. In place of an minus 1, r raised to power n minus 1. In place of an minus 2, r raised to power n minus 2. Then take all these terms in one side, we can write r raised to power n minus 6r raised to power n minus 1 plus 9r raised to power n minus 2 is equal to 0. From here, we can write the characteristic equation. Degree of this recurrence relation is 2. It means in place of this, we can write r square and then power is reduced by 1 and then again with 1. So r square, power is reduced by 1, we have r, again reduced by 1, that is simple constant. So it is r square minus 6r plus 9 is equal to 0. This is the characteristic equation we are getting from this recurrence relation. Now write the characteristic roots. Characteristic roots in this case is equal to 3 and 3. In this case, we are getting a real and equal roots. So we can write solution is of the form first constant root raised to power n plus second constant root raised to power n, but we need to write the different roots. Accordingly, we will multiply n. So that is equal to c1 plus c2n 3 raised to power n. Now we are getting the condition that a0 is equal to 1 and a1 is equal to 6. From here, with the help of these two conditions, we can find the constant values. It says that a0 is equal to 1. It means in this case n is equal to 0 and in this case n is equal to 1. So put n is equal to 0 here. We have a0 is equal to c1 3 raised to power 0 plus c2 3 raised to power 0 into 0. That implies a0, that is 1, is equal to 3 raised to power 0 is 1, that is constant, simply c1, and this term is 0. So directly we are getting the value of constant as 1. Now put n is equal to 1 here. We can write a1 is equal to c1 3 raised to power 1, that is 3, plus c2 3 raised to power 1, that is again 3, and here 1. The value of a1 is 6. That is 3 times of c1 plus 3 times of c2. And the value of c1 is 1. Put it there and evaluate the value of c2. This is equal to 6 minus 3 by 3. That is equal to 1. In this case, the value of c1, c2 both are is equal to 1. And the final solution in this case is equal to 1 plus 1 times of n 3 raised to power n. So this implies 1 plus n into 3 raised to power n is the solution of recurrence relation, this stuff. Let's take one more example. Here we have this recurrence relation. We need to solve this one. As per this one, we have an plus 1 plus an minus 1 is equal to 0. Procedure is same. We will plug an is equal to r raised to power n. So in this case, we can write r raised to power n plus 1 plus r raised to power n minus 1 is equal to 0. Now what is the degree in this case? Maximum index is n plus 1, minimum is n minus 1. This is equal to 2. It means maximum power we will get from here as r square plus. Now the power is reduced by 2 because it is n plus 1, then n, then n minus 1. So it is reduced by 2. So again reduce its power by 2. So we can write r raised to power 2 minus 2 is equal to 0. So this is the characteristic equation. So we can write r square plus 1 is equal to 0 is the characteristic equation of this recurrence relation. So from here r is equal to plus minus iota. Whenever we have the complex form, first step we need to write the solution as first constant, first root raised to power n plus second constant, second root that is negative of iota raised to power n. Then write this into form that is r raised to power n, some new constant cos of n theta plus some new constant b sine of n theta. We just need to find the value of r. R is basically under root x square plus y square. Now what is the value of x and y? Basically x is a real part and y is an imaginary part. If you compare this with x plus minus iota y, as per this one the value of x is 0 and the value of y is coefficient of iota, that is 1. So we can write this is under root 0 square plus 1 square, that is equal to 1. It means the value of r is 1. Now also we need to find the value of cos theta. Cos theta is evaluated as x is equal to r cos theta. So value of cos theta is x by r. What is the value of x in this case? 0. R is 1, that is equal to 0. Value of sine theta, that is evaluated from y is equal to r sine theta. And the sine theta is equal to y by r. And the value of y in this case is 1 and the r is 1. So sine theta is equal to 1. And this is what we need to write at end, that is equal to a times of cos n theta because we have substituted the value of r as 1 plus b times of sine n theta where cos theta is equal to 0 and sine theta is equal to 1. So here we have taken the last question. If the characteristic roots are 2, 2, 2, 5, 5, 9 of the characteristic equation of the recurrence relation of sequence an, then the general solution is of what form? So right now we have the 6 roots. It means there are a 6 constant in the solution. So we can write this as equal to first constant, first root raised to power n plus second constant, second root raised to power n. But both are same. So we need to create as a different one, multiply by n plus third constant, third root raised to power n. Now this is similar to this one. So multiply by n. Now this is again similar to this one. Again multiply by n, that is the n square. Plus fourth constant. Next root is 5 raised to power n. That is different from all other one. So keep it as it is. Plus fifth constant 5 raised to power n as a fifth root. Now this is similar to this one. Create it as a different. So multiply by n. Plus sixth constant and the sixth root is 9 raised to power n. So simplified form of this one is C1 plus C2 into n plus C3 into n square of 2 raised to power n plus C4 plus C5 into n multiply by 5 raised to power n, C6 9 raised to power n. And that is the final form of the solution for the recurrence relation where we are getting a characteristic roots as this.